All right, well, that's pretty much 1 o'clock. So let's begin. So thank you for joining us. My name is JC Arènes. I'm an analyzer specialist with Novatech Analytical Solutions. Today's presentation will be focused primarily on various technologies that exist for the analysis of hydrogen concentrations in gases. These are technologies that are used for online analyses, not for the laboratory. And so the presentation will very briefly show you a few slides about Novatech in case you're not familiar with the company. A little bit of context on why everybody's talking about hydrogen right now, what I call the hydrogen revolution. And then we'll get into the meat of the presentation, which is the technologies themselves. And the way we'll cover them off is a little bit of an introduction. It won't be in depth into how the analyzers work, but more about generalities, what they can and can't do, some of the strengths they have, limitations, and we'll tend to go through them in order of increasing complexity and typically increasing cost as well. And the final section will kind of wrap it all together again and bring it back into what we need to think about when we're looking at doing these types of measurements online in terms of not only the analyzers themselves, but also how does one integrate these analyzers to one's process. There's a fair amount to think about, and this is where certainly Novatech can help you out. So again, a few words about Novatech. This month marks Novatech's 35th anniversary. We were founded in 1986, and from day one, we've always been focused on online process analysis. So we primarily serve three functions. We are first and foremost a distributor. We represent a number of manufacturers of analyzers in Canada, well-known names, leading edge manufacturers, companies such as Siemens, Amitech, Neo Monitors, Guided Wave. Some of them are shown in the images right here. So we act as their representatives in Canada. We have a tremendous knowledge base within the company itself. We're roughly 60 people strong, located across Canada, and really serve as consultants, if you will, or advisors to our clients in the right technologies or the right approaches to take for anything to do with process analysis, emissions monitoring, combustion analysis, gases, liquids, whatever it may be. In addition to the analyzers that we sell, we also engineer and fabricate all of the ancillary systems that go with those analyzers. So you might have an analyzer that's destined for a hydrogen analysis application, but really isn't suited for installation outdoors. And so we would design, fabricate the enclosure and the necessary system to integrate that analyzer into your process. And of course, being in Canada, that also means regulatory requirements have to be met. In particular, we have to ensure that all of our systems meet the Canadian Electrical Code, which means CSA approval or an equivalent, both an electrical approval and potentially, especially when we're talking about hydrogen, it can be a hazardous area approval as well, because we're often dealing with Division 2 or Zone 2 or even Division 1 environments. Canada also has some specific requirements when it comes to pressure vessels and pressure retaining devices. There's something called a Canadian registration number, and in some applications that's a requirement of the systems that we build. Thankfully, Novatech can build CRN rated systems as well. Anytime we build a system for a client, we always welcome the client to our facility to attend the testing that happens at the end of production. It's an opportunity to witness, of course, the performance of the system, but also to speak directly to the engineers and the technicians that built it, get in touch with the technicians that will be maintaining it over time, and ensure an easier handoff to the client. And the final factor in all of this is, of course, long-term maintenance. We have factory-trained technicians that are stationed across the country that are there, of course, to repair things if something breaks down, but perhaps more importantly, are also able to provide preventive maintenance as well, and to make sure that everything keeps running. So they're there. We offer service contracts if necessary, and we also stock quite a tremendous amount of inventory of spare parts to ensure that if something does go down, it can be repaired very quickly. So that's it for Novatech. I wanted to keep it very brief. Let's talk about the subject at hand. Let's talk about hydrogen and why we're talking about it right now. Without question, everything is really being pushed forward by the commitments that Canada has made under the Paris Agreement. We are targeting to be a net zero greenhouse gas emission emitter by 2050. And that's going to take tremendous change in the way we do things. And without a doubt, hydrogen is going to have to play a part in that. So in December of last year, the hydrogen strategy for Canada was released. And there's a number of recommendations and strategies are outlined within it. But it's clear that hydrogen as an energy source is going to play a key role if we're to meet our net zero targets. So that would be hydrogen as a fuel source for transportation, potentially for power generation, directly combustion for heating and buildings. And as is the case today, and it will always be the case most likely, a feedstock for industry as well, because hydrogen is a building block for other materials. The most one that comes to mind readily, of course, is fertilizer manufacturing. Ammonia production is a tremendous user of hydrogen as a building block. Within that strategy, the vision for hydrogen in 2050 highlights some very interesting goals or things that may be achieved if we follow this path. Some of the ones I've highlighted here, potentially up to 30% of Canada's energy would be in the form of hydrogen if we're to follow these recommendations. Canada would be positioned as a top 3 global producer of clean hydrogen, producing over 20 million tons per year of hydrogen. And that is largely due to the fact that we have access to a ready source or many ready sources of clean energy within the country itself. And there's also talk of converting over 50% of the natural gas usage in Canada to hydrogen usage. So that would involve dramatic changes, certainly blending of hydrogen into existing natural gas pipeline, something that's already being explored right now. And we're in discussions with a number of the pipeline companies that are very interested in doing this, and potentially also the building of dedicated hydrogen pipelines. So all of these goals combined certainly would have a tremendous impact and could amount to as much as a 190 megaton per year reduction in greenhouse gases. So it's all very interesting to talk about this, but the interesting thing about hydrogen is, despite being the most abundant element in the universe, it's not really very common on Earth or in naturally occurring. So we actually have to manufacture it. And there are 2 main processes for the manufacturing of hydrogen. The first is steam-methane reforming. And this is already by far and away the most common production method for hydrogen, certainly in Canada. And this is actually very prevalent in Western Canada, and that's largely because of the ready source of methane. We are basically taking methane and under certain conditions, combining it with steam at high pressure with catalysts and forming carbon monoxide and hydrogen. Depending on the source of the methane and whether or not we combine the process with some form of carbon capture, we are either producing gray hydrogen or better still, blue hydrogen, which is a little bit better in the sense that we are actually capturing that hydrogen and not, or pardon me, carbon and not releasing it. The process is as follows, essentially 3 stages. I won't go into too much detail, but they're progressively converting more and more of the methane into the hydrogen. In the first stage, we combine the methane with steam, convert quite a bit of it, but not all of it. So then we introduce air, which brings oxygen into the equation. Now we're converting the methane into carbon monoxide and more hydrogen. So now we have more hydrogen. And then the final stage is basically shifting. It's known as a shift converter under certain conditions and catalysts, shifting the CO to combine with water to form more hydrogen still. So at the very end of the process, we have carbon dioxide and hydrogen, and of course nitrogen from the air, but we can actually remove the carbon dioxide in an amine wet gas scrubber. And this is essentially the process that we see in a lot of facilities already that exist, certainly in the fertilizer manufacture, but also potentially in refining applications as well. The other big technology or most commonly used technology for hydrogen production is electrolysis. And this is the one with tremendous promise from the standpoint of being a much greener technology, in that we're not actually using methane to produce the hydrogen. We're basically splitting water for all intents and purposes. We depending on the source of fuel, if you will, or the source of the electricity that we're using, it ranges in whether or not we're producing a gray, pink from nuclear power, blue, that's hydrocarbons with carbon capture, or green if we're using a renewable source of electricity. But we still have to remember that even when we produce green hydrogen, there is still a carbon footprint associated with the generation and transmission infrastructure for that electricity. So it's never a free ride. How electrolyzers work is as follows, and I'm showing an example of what's known as a PEM electrolyzer here, or a polymer electrolyte membrane electrolyzer. We have a vessel with water with two electrodes, a cathode and an anode, and a separation between them, this membrane. And what happens is at the anode side, as we apply electricity to these electrodes, at the anode side, we release the oxygen from the water, and we separate the hydrogen into positively charged hydrogen ions and electrons, which travel up through the circuit. The hydrogen ions are able to pass through this membrane. It's selectively permeable, and then recombine with the electrons on the other side and come out as hydrogen gas. So on one side of the cell, we have hydrogen gas being produced. On the other, we have oxygen gas. And so immediately we can see that there's an opportunity for an analysis here. We wouldn't want those two gases mixing together. If we mix hydrogen and oxygen together, we potentially create a flammable or explosive gas. So the opportunity to measure for the presence of hydrogen in the oxygen and conversely oxygen in the hydrogen is certainly justifiable. The flip side to that is, how do we now use the hydrogen that we've produced in a non-combustion application to generate electricity? Well, the short answer is by using a fuel cell. And a fuel cell essentially is that electrolyzer backwards. We're now producing water as opposed to splitting water. So a fuel cell is like a battery that runs continuously as long as the fuel is present. On one side, we feed it with hydrogen. On the other side, we feed it with oxygen from air, and the electric current is generated as the hydrogen dissociates into positively charged hydrogen ions and electrons. And these positively charged hydrogen ions will combine with the oxygen to form water vapor. So the fantastic thing with fuel cells is that there is no pollutant created in the generation of the electricity. So it's certainly where we see the potential for hydrogen being used as a fuel for transportation vehicles. This is one potential way of using it. So that was a brief introduction to the why. Why is hydrogen such a hot topic today? And certainly that could be a presentation in and of itself. But where Novatech shines is not on that side. It's really on you want to measure hydrogen, we can help you with that. So we'll go through the various technologies here, again, in order of increasing complexity and perhaps capability as well, but also increasing cost. One by one, there's 6 different ones that I want to highlight today, and then we'll kind of wrap it all up in the summary at the end. So the first technology we'd like to present is what's known as a solid-state sensor. And these were originally developed by the Sandia National Labs and the US Department of Energy. And what they are essentially is a palladium nickel alloy that can be formed into a thin film, or basically a chip sensor that only reacts or is only affected by the presence of hydrogen. There are other components that can have an impact in the catalyst's ability to do what it does. And so there are coatings that can be applied to these sensors. And certainly temperature control is critical. So the sensor must be very tightly controlled within the analyzer itself. But one of the nice things about this is that they are specific to hydrogen. Hydrogen is the only thing that causes what we're going to see in the next slide, the change in the physical property that we're monitoring. And there's no need for anything else. There's no reaction happening. We don't require oxygen for the sensor to work. There's no carrier gas. So from that perspective, they are very interesting. So we see here a representation of this palladium nickel catalyst matrix, if you will. And what happens is at the surface of this structure, the hydrogen atoms are basically dissociated into hydrogen molecules are dissociated into hydrogen atoms. And the hydrogen atoms will actually be absorbed into the palladium nickel matrix. And as more hydrogen atoms are absorbed in, the resistance of that structure changes, the electrical resistance. And we get a linear response from about 0.5% hydrogen all the way up to 100% by volume. The nice thing is this is a reversible phenomenon, if you will. If I take hydrogen away from the gas, then the hydrogen atoms that are in the matrix will come out of the matrix and form hydrogen molecules again. If I increase the number of hydrogen molecules in the gas, then more of them will go back into the matrix. So it's a reversible reaction, and it follows basically, it trends with the conditions of the gas at the surface. And so this matrix, if you will, this palladium nickel alloy is mounted on a chip, and that can then be adapted into a form factor that's useful for our purposes of doing a process gas measurement. And they look something like this. We can see them here, for example, where the sensor is mounted at the tip of a probe and potentially could be used in an in situ, in other words, directly inserted into the process, or they can be mounted or integrated into a flow-through device where the electronics are housed in this hazardous area rated enclosure that allows the gas to flow through it on a continuous basis and monitors the condition of, or the hydrogen concentration within the gas. Strengths and challenges. The most obvious strength is the fact that it's hydrogen specific and it's relatively low cost. So those make it an easy way to add a hydrogen measurement maybe to an existing analyzer system. We talked earlier, for example, about the pipeline companies that probably already have analyzer systems. They're monitoring for components within the natural gas pipeline. They're looking at BTU, they're looking at H2S concentration, they're looking at moisture. If they wanted to add a hydrogen measurement, this might be an easy way to do it. In terms of challenges, we do have to be cognizant of the limits when it comes to some of the contaminants that can cause issues with the sensor. Similarly with oxygen as well. If oxygen is present, we do have to be careful in the selection of which sensor we're using. There are also sensors which are designed or work best when hydrogen is always present. And if we take the hydrogen away, the sensor may have may need some time to come back up into operating function. And because, as I described it earlier, as we increase the number of hydrogen molecules in front of the sensor, this is basically a partial pressure device. If I increase the pressure of the gas in front of the sensor, it's essentially the same as cramming more molecules into that matrix, and therefore I can get a change in the reading. So they are pressure and temperature limits to the sensor, but also there are pressure and temperature compensation requirements. I have to be able to compensate for those changes in pressure and temperature in order to get a correct reading. The next technology we'll talk about is thermal conductivity. And thermal conductivity is a physical property of any pure substance. Any pure substance has a known and quantifiable ability to take away heat or transmit heat. So what's interesting is that hydrogen is by far and away the gas with the highest thermal conductivity. And so that makes it very different from everything else. And because it is so very different to everything else, we can look at the overall thermal conductivity of a gas. And if we have a good understanding of what it's made up of, and primarily if it's a binary mixture, 2 components only, we can use that thermal conductivity to approximate how much of it is hydrogen. And so that's the concept of how a thermal conductivity analyzer works. The way we measure the thermal conductivity is essentially we look at the gas's ability to conduct heat. So we have a sensor that's made up of hot wires. One side is exposed to the target gas, or the sample. The other side is exposed to a constantly flowing reference gas. And it has to be different, of course. And we compare how much heat is taken away in the sample side versus how much is taken away on the reference side. These are connected in what's known as a Wheatstone bridge, and that allows us to continuously compare the change in resistance as we take away heat from one side versus the other. The way the sensor can be arranged varies from manufacturer to manufacturer. They can be micro-machined directly onto a silicone chip, which has certainly tremendous advantages in terms of speed of response in an analyzer. But of course, that for applications where maybe we have corrosive substances, we would probably use the more traditional sensor where we can actually protect the wire elements from the corrosive nature of the gas. Form factor, these are extractive analyzers. And when I say an extractive analyzer, what I mean by that is that I must bring the sample to the analyzer. I can't mount the analyzer directly onto the process I'm trying to measure. And so they're available in either a rack mount or a field mount configuration such as this. These can be combined into an existing analyzer system quite easily. We often see analyzer systems made up of rack-mounted components such as this. They're relatively inexpensive. This technology is not expensive, but really the limitation or the challenge with any kind of thermal conductivity analyzer is that it is non-specific. It measures the thermal conductivity of the overall gas mixture, which means we have to have a fairly good understanding of what that gas mixture is in order to draw any conclusions about the composition or the amount of hydrogen that might be present. Similarly, depending on what that background is that we're trying to measure in, there may be an impact on how high or how low I can go in terms of my hydrogen measurement. So there's never a one-size-fits-all answer, as you're soon going to find out, I think. So the next two technologies that we're going to talk about are both based on spectroscopy. And specifically near-infrared spectroscopy. And just as a reminder, for anybody who may not already be familiar with it, what we look at in spectroscopy is basically the absorption of energy at a given wavelength. So we emit energy at a certain wavelength, and we know that at that wavelength, the only thing that can happen to it is that based on how much or how sensitive a specific molecule is to that energy, a fixed coefficient exists, and the only thing that will, or what will impact how much energy gets absorbed is the distance that I travel through that gas and the concentration of the molecule of interest. And so I can use this relationship to back calculate or to derive concentration. If I keep the other variables fixed, then concentration is the only one that changes. So that's very good, but the problem is, in reality, most of the time I have real problems. There's spectral overlap. So if I look at, for example, H2S and water vapor in the infrared spectrum, we can see that the absorption regions are just all over each other. And so there are real limitations that one has to be aware of. One of the ways that we deal with this, for example, in emissions monitoring applications, is we often do the measurements cold dry. And what that means is we remove the water from the sample. If I remove the water, I can more easily measure the other components because that interference is gone. But sometimes I can't do that, or I don't want to do that. Sometimes what I'm trying to measure is the water, or sometimes what I try to measure might leave if I remove the water as well. So hot-wet measurements might be useful. So how do we deal with that? Well, one way we can deal with it is by using a different method. Instead of looking at what are known as instead of using optical filters, we can use tunable diode lasers. And the benefit of tunable diode lasers really comes down to this. The laser spectral line width is a fraction of a nanometer, is incredibly narrow. And because I can choose at what wavelength I emit my laser energy, I can basically scan across a single absorption line for the component I'm trying to measure. And so you might think that this is the solution to everything. It isn't. There are only certain molecules that absorb in the regions where we can use TDL technology. There are still sometimes overlapping peaks, so we do have to pick and choose the applications. But when we have the right combination of, I've got a good line, I don't have interference from another gas, it's a tremendously powerful technology. And one final thing to mention is that the ability to scan the laser across the peak of interest gives me 2 bits of information that are very useful. Of course, it gives me the absorption at the center of the peak, which is basically the function of how much gas is present, but it also gives me a baseline reading on either side of the peak. And by monitoring the baseline, I basically do a 0 calibration on every scan. And so these are tremendously robust and reliable and stable analyzers that typically don't need to be calibrated. Form factor varies. For the hydrogen measurement, we have 2 different form factors available. One is what we would call an in-situ technology, where we have a laser on one side and a detector mounted on the opposite side of whatever our process is. It can be a pipe, it can be a vessel of some kind. The pipe can be small or it can be very large. It depends. So mounted directly to the process, and that means that we're monitoring or measuring at the process conditions. So whatever's happening in the process, if the temperature changes, if the pressure changes, we see that directly in the analyzers. We do have to compensate for that. The one thing that's important to note, though, is this: the optical path length is dependent on the vessel itself. The other form factor that's available for this type of analyzer is an extractive one, where we have what will be called a Harriet cell, where we're bouncing the laser back and forth inside a cell here. So the sample has to be introduced to the cell and brought back out again. And that means that we can mount the analyzer where it's most convenient in a more accessible location potentially. And it means we can have a fairly long path length. It's fixed at 11 meters, which allows us to measure at lower concentrations. But it is extractive, so I do have to ensure that the sample is conditioned to the way the analyzer is best able to deal with it. In other words, I have to keep it dry. I have to make sure that the temperature and pressure are at the right values for that type of measurement, all of those types of factors. So, strengths and challenges. When we talk about either of these, whether it's the in-situ technology or the extractive one, they are hydrogen specific, which means you're not going to get a false reading based on something else. If we're in situ, the benefit is that there is no sample system. We are monitoring exactly what's happening in the process or in the pipe without any change to the sample itself through the sample conditioning system. It also means that the speed of response will be tremendously greater. In terms of challenges, however, when we mount something directly onto the process, we have to ensure that the optics in these analyzers stay clean. So it will require some kind of purge gas to ensure that the windows don't get fouled by the process itself in any way. It also means that we require 2 nozzles on the process, which means that we may not be able to install something until a shutdown occurs of some kind. And we do have limitations in terms of the process itself. If I'm trying to measure at very high concentrations on a huge process, it's not going to work. I'm going to have far too much absorption in the process. Likewise, if I'm trying to monitor a low concentration on a tiny process, it's also not going to work. When we talk about the extractive technology, similar strengths in that it is hydrogen specific, but because we have the ability to have a very long path length of 11 meters, we have a lower detection limit. We can get down into parts per million quite easily. But it is extractive. We need a sample conditioning system. It's not a heated analyzer, so we have to ensure that we don't have any issues with low dew point samples or components of any kind. So cavity ring-down spectroscopy, let's go back up. Similar to absorption spectroscopy with a tunable diode laser. It's still using a tunable diode laser source. That hasn't changed. But And generally, we're able to see the same gases because we're essentially using the same types of lasers. What's different is in the way we interpret the signal from that TDL. So the way this works, we fire the laser into the source, and we have highly reflective mirrors at both ends. So as the laser bounces back and forth, it interacts progressively more and more with the sample, and more of the energy gets absorbed at the wavelength that we are emitting at. And so what happens is the laser intensity a little bit leaks out with every pass, and the laser intensity will decay over time. That time decay, that time that it takes to go from the full intensity laser down to a value where we can barely see it anymore, is a function of the concentration of the gas inside the cell. As the laser light bounces back and forth inside the cell, it will decay. When we have no target gas of interest, we have a very long decay. It takes a long time for the light to extinguish. When the target gas is present, we have a much faster decay. The difference in time between these two signals is proportional to the gas concentration. And so we are able to use this technology because we're bouncing that light back and forth inside the cell, and very little, we have a high intensity light and we're only allowing a very small amount to leak out. That effective path length can be hundreds of kilometers. And that means we can use this technology to measure at very, very low concentrations. Parts per billion, no problem, even parts per trillion in some applications. One other thing worth mentioning is that these analyzers will also use what's known as a reference cell. And that's really a function of the fact that we're trying to measure at very low concentrations. It's important to know that we're looking at the right area, that we're emitting our energy at the correct wavelengths. So the light from the laser is split between the sample cell and the reference cell. A small portion of it goes through the reference cell. That reference cell contains the analyte that we're trying to measure. And so the detector over here will always confirm, yep, we're looking at the right place. I'm seeing that there's absorption. The laser is emitting at the correct wavelengths. And so this characteristic curve that comes out of it, this time decay, is the function that allows us to measure at very low concentrations. We measure hydrogen in an interesting way. With these analyzers, we actually don't measure the hydrogen directly, unlike the tunable diode laser analyzer that we saw earlier. In this case, we actually dry the sample, remove any traces of moisture from it, and then combine it with oxygen from air to form moisture so that we have a known concentration of moisture to hydrogen. It's a 1-to-1 ratio, basically. And then we measure the moisture. We have very high sensitivity for the moisture measurement. The wavelengths of interest are very powerful. We have good signal at those wavelengths. So in terms of technology and strengths and challenges for the CRDS technology, the strength is the sensitivity. That ability to measure down to parts per trillion is very hard to match with any other technology. It's also a calibration-free technology, much like the TDL we saw earlier, and it's a NIST traceable technology. We can actually put NIST traceable standards within it and factor that into the correction of the analyzer or the calibration of the analyzer. From a challenge perspective, it does require a source of clean, dry air or a mixed gas of nitrogen and oxygen. And the technology, while it excels at very low concentrations, it doesn't work at higher ones. So we're limited to measuring at that very low end. And finally, as with many of the other ones, it is extractive. I have to bring the sample to the analyzer. The next two technologies that we'll talk about are both what I call separation techniques, in that they take our mixture of gases and we're trying to ascertain the concentration of one component or maybe multiple components, but we're trying to kind of separate it out from the herd, if you will. And so these techniques, and gas chromatography is the first one, take a mixture and separate it out into its individual components. And in a gas chromatograph, we do that physically. We actually will take the sample and through a series of components within the analyzer itself, run it through separation columns so that we extract the components one at a time from the sample that we've injected into the analyzer. So there's a carrier gas that pushes along our little blob of sample that we've injected into it. As we go through the various columns, each of the individual components in the sample, or series of components sometimes, will come out of that column individually over time, which means that whatever detector we've got on the end here will see one component at a time. So for example, when we're separating hydrogen from the mixture, at a predetermined time, we know that hydrogen will come out, and we know that the area under the peak that's generated at the detector is proportional to the concentration. The only thing it can be is hydrogen. So it's tremendously powerful technology in that respect. It allows us to extract and measure information from complex mixtures that we might not be able to do spectroscopically, or certainly not with a standard thermal conductivity analyzer. Having said that, one of the detectors that we use in a gas chromatograph is a thermal conductivity detector. But keeping in mind that because we've separated everything, we are dealing exclusively with a binary mixture. I have whatever my component is that's coming out and the carrier gas. So it's a two-component mixture, which means I can now use a thermal conductivity detector to full effect, because it will see concentrations of just about anything that is different than whatever the carrier gas is. And therein lies the little hiccup when we want to do a hydrogen analysis. Most process gas chromatographs that are currently out in the field, or certainly in the last few years, most of them use hydrogen as the carrier gas. And that's because of that very fact that it has a big difference in thermal conductivity with everything else. Makes it a great reference gas, or comparison, if you will, in that thermal conductivity detector. If I want to measure hydrogen, then I have to use a different carrier gas. And so that means that I either have a dedicated GC or a dual gas GC set up so that I have nitrogen, for example, as my carrier gas for the hydrogen analysis, and then a separate train that maybe measures the other components that can also still use hydrogen as its carrier gas. There is an increased complexity when we want to do hydrogen analysis. It also means, because GCs are very much hardware specific, when we buy a GC, when we build a GC or gas chromatograph for an application, we build it for that specific application. So we take the gas composition that a client gives us, and they say, I want to measure these components in these ranges, in this background. The scientists at the manufacturer will look at it, the application specialists, they will choose the various columns and the way they arrange it, the way the gases flowed throughout the GC to do that specific analysis. If we want to make a change to that analysis, for example, I now want to add hydrogen to my existing GC, it requires changes to the hardware. And so that is a cost that must be taken into consideration for retrofit applications. However, tremendously powerful. It can measure multiple components. We can measure 1, 2, 10, 20. It really depends on what you want to do and how long you're willing to wait for those results. The more components we measure, the more complex the analysis, potentially the more time it takes to do. It is capable of operating hot wet, and I'll talk about the differences between hot wet and cold dry a little bit later, but that means that we're not altering the sample in any way. And it is capable of extracting hydrogen from complex mixtures, which does make it very powerful. However, as we've just explained, different carrier gas if we want to do a hydrogen analysis. Infrastructure requirements, the GC, as you see it, can't be just put into the field. It needs to be in a nice climate-controlled environment. We need to be able to access it for maintenance. So typically we're talking about putting these in buildings, analyzer buildings or shelters that might be installed in the field, and that means that there's a fair amount of cost associated with that. Utility requirements, it needs carrier gas of some kind. It might need a fuel gas depending on the type of detector that's used. It probably needs instrument air for valve actuation. So there are a number of things that are required to operate a GC. And cost. As we go down the list, we're getting into more and more expensive technologies, but of course the capabilities are increasing as well. So the next technology, and you might recognize the picture, is mass spectroscopy. And I use the same image because in my mind, that's one of the interesting things, is that once again, this is a separation technology. It takes a complex mixture and through a different technology separates it into individual components so that we can analyze them one by one. The difference is in the separation technology. In a gas chromatograph, we do a physical separation using columns. These columns basically allow the sample to flow through, or the components to flow through at different speeds, which means they come out at different times. In a mass spectrometer, we're relying on essentially what's known as a mass to charge ratio. So this is what a mass spectrometer looks like. We have some means of bringing the sample to it. And the first thing that happens is pressure reduction. Mass spectrometers operate under very high vacuum, 10 to the minus 5 torr, something along those lines. So very low vacuum. We then ionize the sample to create positively charged ions. We then separate the sample in the mass filter, which I'll show you in a minute. And then we have the detector that looks at those different components. So that first stage is pressure reduction. Then our sample, our mixture of molecules goes in to a very strong electrical field where we strip away electrons and create positively charged ions. So now these positively charged ions are fired down into the next section, which is the mass filter. Because they're positively charged, I can manipulate them now. Mass separation is done primarily in one of two ways. In the market for online process mass spectrometers, these are the two technologies that you'll see. They effectively do the same thing, they just do it a little bit differently. Quadrupole and scanning magnetic sector. This is what a quadrupole mass filter looks like. So here's our ion source at the beginning where we create our positively charged ions. And then these four rods here we have the ability to control the radio frequency field and the DC current that's applied to them. And that allows us to basically aim certain mass to charge ratios into our detector. As we alter those parameters, the DC and the RF parameters, we aim different positively charged ions into our detector. So we can choose which ions we want to look at. In a scanning magnetic sector, same concept, but we're using an electromagnet now. So as our ions are fired out of our ion source, our positively charged ions travel down towards this electromagnet, and the field strength that we apply to this electromagnet will divert the beam path. And by varying this field strength, we change the arc of the field path. So different ions will hit our detector at the end. And there's an illustration here. As we change the field strength, we have different mass charge ratios hitting the detector. I think this is a good representation. It makes it clear how it works. What does that all mean? As we look at the different molecules, and I'm not showing hydrogen here for this example, we see that the molecular weight of the molecule is potentially problematic because nitrogen has the same molecular weight as carbon monoxide. And so if I were to rely on only looking at mass to charge ratio 28, I wouldn't know whether or not I'm looking at nitrogen or carbon monoxide or both. But one of the things that happens within that ion field is we also create fragments. And the fragmentation pattern of these molecules is well known and understood. We know where the fragments for nitrogen are. We have, a big peak at 28, but we have another peak at 14. Similarly for carbon monoxide, big peak at 28, two other peaks at 12 and 16. And because we know the fragmentation patterns and we know the relative strengths of the fragments to the main peak, we can use math basically math to separate out what each individual component is. And then if I throw one more in, for example, if I throw in carbon dioxide, I see that I get another one here, another peak at 28. So what this means is that, yes, it's a tremendously powerful technology, but it means that calibration can become interesting. We have to calibrate not only for the components we want to measure, but we also have to calibrate for the components that may also be present in the sample. So it can be more complex from a calibration perspective as compared, for example, to a GC, where we really only look at the components we want to measure. So in terms of strengths, linearity and stability, incredibly linear. We can measure from parts per million all the way up to percent levels with the same calibration. It can measure multiple components. It can operate hot, wet. It is hardware agnostic. We don't change the hardware when we want to change the components we want to measure. We simply change the programming and the calibration, which is interesting from that perspective, different than, say, a GC again. And speed, incredibly fast, seconds, an analysis in a matter of seconds. However, calibration can be complicated. Just like a GC, it wants a nice, clean, dry, warm environment to sit in, and cost. They're not inexpensive analyzers. Okay, so barring the fact that we wasted a couple minutes there, we do still have a few minutes left for the system considerations, where I'll talk a little bit about some of the points I made along the way. And the first is, let's be sure we understand what in situ versus extractive means. When we say in situ, the analyzer is mounted directly on the process. And I'm showing a chimney here for argument's sake. It doesn't have to be that. It can be a pipe. It can be a vessel. It doesn't really matter. But in situ measurements are done directly on the process. Extractive measurements, as the name implies, pull a portion of the sample, bring it to a sample conditioning system that then introduces them into the analyzer. And this is where the big difference between these two lies. If we could do all of our measurements in situ, we probably would. It's simply, better from the perspective of being able to do the measurement directly in the process, no sample system. However, we can't do them all in situ. Technologies that can measure in situ are limited, lasers being one of them, for example. And also what's happening in here may preclude our ability to do that measurement in situ. If, for example, this is, a stack and there's a fair amount of smoke, then my laser may not work. I may not be able to see from one side to the other. If there's a lot of condensing moisture, I may not be able to do the measurement there. If there are corrosive elements, if the pressure is too high, if the temperature is too high, et cetera, et cetera, et cetera. And so the reality is the vast majority of analyses are done in an extractive fashion, where we control the conditions of the sample so that they suit the analyzer. Some of the things to keep in mind: sample dew point. We talked about it earlier. And the approaches when we're talking about extractive analyzers are basically two. We can either control the dew point and say, I'm going to change the dew point of the gas by chilling it or using some kind of dryer system so that when it goes into my analyzer, there is no risk of condensation occurring. So my sample might be coming out of a process with a dew point temperature of 70 degrees C. I bring it into my sample system, I chill it so that I drop out moisture, and now my dew point temperature is roughly 4 degrees C. And it goes into the analyzer with no risk of condensation occurring in the analyzer. Or the other approach is I stay away from the dew point. If my dew point temperature is 70, I can simply run everything hot well beyond the dew point temperature to ensure that everything stays as a gas. 70 degrees C dew point temperature, maybe I run everything at 130 degrees C. I bring everything in heated sample lines, a heated sample valve going into a heated analyzer so that I'm never near the dew point temperature and I have no risk of condensation. Two different approaches with pros and cons. This may be more complex, but I haven't altered my sample in any way. Whereas a cold-dry system, while relatively simple to implement, alters the composition of my sample gas. If 30% of my sample was water and I take out the vast majority of it, I have greatly increased the concentration of all the other components that the analyzers see. I have to be able to correct for that. Sample pressure. We talked about pipelines earlier. If a pipeline is operating at a relatively high pressure, me bringing the sample out of that and into an analyzer that is designed to operate at near atmospheric pressure presents a challenge. I have to be able to reduce the pressure in a controlled way and not lead to problems like Joule-Thomson cooling and freezing up my regulators, things of that nature. The other issue that I have to think about is if I have to now return the unmeasured sample or the unaltered sample back to the process, how am I going to do that? I either have to find a low pressure point within the plant, or I have to have the ability to bring the pressure back up again to be able to re-inject it into the process. We have to be cognizant of sample hazards. If we're measuring hydrogen in a sample, then we are by nature dealing with a sample that contains flammable components. So we have to think about the flammability of the sample. What are other potential hazards within the sample? Does it contain H2S, for example? When we think about natural gas pipelines, if H2S is present, I have to be aware of that and know that if I'm putting my sample system inside a box, I have basically a contained environment where concentrations of hazards such as hydrogen, H2S, or others could build into dangerous levels. So I need to monitor for leaks. I need to monitor the condition within the enclosure. So for example, I might be purging that enclosure and monitoring the exhaust with a gas detector to ascertain whether or not there is a leak within the enclosure. These types of things have to be part of the system design to be a safe and effective system. We have to think about what the sample will do to the components within our system. And certainly the pipeline companies are well aware of this, and I'm sure thinking about the fact that hydrogen does things potentially to materials and metals. We've heard of hydrogen embrittlement, for example. So they have to be cognizant of that. We, as designers of extractive sample systems, have to be aware of the hazards that could be created by the sample itself, whether it be changes to the metallurgy, whether it be corrosive components within the sample. If we're talking about, for example, hydrogen from a chloralkali plant where they're producing chlorine, hot, wet chlorine gas potentially, the materials have to be suited to the application at hand. We have to think about how we validate the performance of our analyzers. It's one thing to install a tunable diode laser directly onto the process, but how do I know it's working properly? I can't flush the entire process and fill it with some kind of cal standard. That's not practical. So I have to have an ability to test the analyzer without having to remove it from the process and do anything like that. So that's something that has to be designed into the system as well. The other thing to think about, which we don't often think about, is how do I calibrate or test the performance of an analyzer that's measuring very, very low concentrations? We talked about parts per billion, parts per trillion. The ability or the access to good quality standards at those concentrations is very, very, let's say, variable. And so it may be more practical or maybe wiser to use good quality standards and blend them down to the concentrations that we need. So there are complexities involved with these types of measurements, especially at the very low end. So in conclusion, and I'm right on time except for question period, we have a range of technologies available in the market today, but no one technology will address every application. We can probably address all applications, but not with one technology. And the reason why no one single technology will work is all of the things, the challenges we talked about earlier, the range, the interferences that might be present, the conditions of the process, and the budget. So consideration has to be given to all of these things, and more importantly, I must stress that consideration must be given to the costs of the integration of the analyzers with the process. Often these are greater than the cost of the analyzers themselves. In fact, they can be many multiples if we're talking about a building, for example. So my suggestion would be to anybody who's looking at any kind of analyzer project, not just for hydrogen, is bring in consultants like Novatech or experts like Novatech at the earliest possible stage. And that is so that we can help you define the budgets properly, give you an idea of how much the costs will be, so we don't get halfway down the line and realize that we've budgeted a certain amount and in reality it's going to cost double or triple that. So I thank you very much for your time. If there are any questions and you're willing to stay on, I'd be more than happy to try and answer them now. No questions at this time? All right. Well, thank you very much for joining us. You're more than welcome to reach out to us. Again, you have our contact information. If you'd like any more information or would like to talk about any of this presentation, or if you would like us to do a presentation for your company on a specific subject, by all means, we are more than happy to do that. Thanks very much, everybody.